Hi, this mini lecture topic is multiplier. In order to derive a multiplier structure, and I will start with paper and pencil method for multiplying two binary numbers. Let's assume you've got 6 times 5, and this is a mark of arithmetical multiplication, not logical one. So in order to multiply, we take consecutive bits of number b, and multiply bit by bit. 1 times 0 gives you 0, 1 times 1 gives you 1, and so on. If you multiply by 0, zeros occur in the next row, and the number a in the second row. 1 times 1, and shift. That is a very important operation to shift the number in the results in the consecutive rows. And then I must add together, yes, all the rows together. 0, 1, 1, 1, 1 is the result. Okay, and two problems arise. In order to implement it, you must map this operation bit by bit multiplication with logic 1, and then you must replace addition of multiple rows, multiple numbers in one step by consecutive addition of two numbers, because we know already full adder cell and how to construct other having arbitrary number of bits, so we are ready to do it. So instead of doing it in this manner, let's try to do it in a smaller steps, but always the same steps, okay, for each bit. So for what we do for each bit, we multiply ai times bi. Let's consider this operation. Let's put the values of these into truth table, and arithmetical operation 0 times 0, 0 times 1, 1 times 0, and 1 times 1. It is exactly the same as AND operation, logical. So arithmetical multiplication of 2 bits, yes, 1 bit of times another one, is exactly the same as logical operation. So we can use AND gate to multiply the bits of the numbers. And so wipe it down. What's the next problem is to add it. Okay, so how to add? We must have partial results from the previous lines. Let's have a look. We must add here to zeros. So add here. We don't see the second, we can assume that the second argument is 0. And here, this is a result, we add again, and we add again, and get the final result, okay? So we will have partial results here after addition. But before addition, we must perform multiplication by 1 bit, mul, and also shift. And because, yes, and position 0 gives you shift by 0. Position 1 tells you that you must shift by 1, and position 2, and so on. Okay, so let's try doing this in general. Let's wipe it out, and let's assume that you've got 2 3-bit numbers. One is A2, A1, A0, and the second is B2, B1, and B1, and B0. And your task is to multiply these using the new algorithm, a little bit different than the usual one. So let's assume that your partial at the beginning, your result partial is 0. That's a good assumption, and then you multiply in this line by b0. So you've got a0 times, but times can be replaced by dot. It is an AND, simply AND function. A0 times B0, A1 times B0, A2 times B0. And shift is 0. So it is a mul shift and then add. So in order to add, you use full adder. So let's put full adder cell here. But if we go to the structure, to the logic diagram, you can also put gates to perform multiplication, logical one. Okay, and simply by putting a gate here, and then you must add this product with earlier result. Previous result was 0. So this is the first line. Yes, do it here as well. So what you need is a full adder cells, which are 3 in this line. You must connect them properly to get the proper result. And result, as you know, in general, will have 4 bits. If you add 2 3-bit numbers. Here you put 0, okay, no carrier, no input carrier. And that's it. And you repeat the same procedure in the second row. You simply multiply using AND and shift, of course. It is AND gate, another AND gate, and another AND gate. But the signals are B1 times A2. Here you've got A1 and B1, and here you've got A0 and B1, so it is a multiplication by B1. Here it was by B0. Okay, and again you must use full adder cell to add together the previous result with the current. Here you don't have current result, so this will be transferred to the output. FA, there are 3 more FAs in the second row, FA, and also here you've got FA, and you must connect them in the same regular manner, and you put 0 as well here. Okay, so looking at these, the structure is very regular. You can derive a multiplier cell, let's say mul cell, iterative cell, which consists of a full adder cell, well-known full adder cell, and a single gate. So if you equipped full adder with a single gate on one of the inputs, you will have a multiplier cell. Okay, and you can see this multiplier in this slide. You've got the internal structure of multiplier. It is called, yes, and this we can call it M. It is a multiplier cell, and you can see this as a for bit by bit multiplication, and then addition. Okay, and shift is simply realized by shifting, by putting the full adder cells, the multiplier cells, in the consecutive columns, yes, by shifting them. And the overall result, 6-bit, it is simply 2 times 3, where 3-bit as the 3 is the number of bits of each of the numbers. Okay, so if you multiply 3-bit number by 3-bit number in general n-bit numbers, you get 2n-bit result of multiplication. It's 2n-bit product. Try at home, repeat the same procedure of deriving. Okay, try to draw this diagram and think about this algorithm: multiply with shifting and adding. and again multiply by with shifting and adding, and so addition is performed after each multiplication. Okay, not as in method, you know, and addition is at the end, addition of multiple rows, because we don't have such other. We have only other which can add two numbers together. Okay, try at home as a practice. For practice, simply deliver the full diagram, the complete diagram of 3 by 3 bit multiplier. Thank you.